Dear conference participants, the European Organization for Nuclear Research, known as CERN, is an intergovernmental organization that operates the largest particle physics laboratory in the world. Many activities at CERN currently involve Operation the Large Hadron Collider and the experiments for it. In 1 second, the LHC has 600 million collisions, which corresponds to 1 million gigabytes of raw information. With the help of special software, this data is converted into readable objects and stored for further analysis. More than 12 petabytes of new data are generated each year through ongoing experiments, helping CERN scientists advance science and answer questions about the fundamental laws of nature. An important fact for our study is what the European Centre for Nuclear Research report, the discovery of a huge amount of data obtained at the Large Hadron Collider. It is noted that some data are presented in raw form, which they are available to CERN researchers. Other information is presented in a processed form, which makes it suitable for use, in particular for educational purposes. Both students can use valuable information and professional scientists involved in elementary particle physics. The CERN Data Open Data Portal is an access point to a growing range of data generated through research conducted at CERN. It distributes saved results from various research activities, including the accompanying software and documentation what is needed to understand and analyze the data. In this regard, the questions arises of the effectiveness of using CERN open data in the process of conducting practical work in elementary particle physics as one of the methods for generating knowledge about experimental methods for studying modern elementary particle physics. In our work, we use data from a compact muon solenoid. The compact muon solenoid experiment is one of the two large general-purpose particle physics detectors built on the Large Hadron Collider at CERN. Validation compact muon solenoid open data is through successful reconstruction of the iSpy Y and Z DC channels for comprehensive statistics. Although they cannot directly observe the particles formed in the collision, where DC products leave signals in the CMS subdetectors. Special software uses these signals to reconstruct the DC products, which scientists classify into different families and physicists call physical objects. CMS learning resource is a collection what includes learning resources with the public CMS data. The items in this collection are suitable for educational purpose. For training purposes, complex raw data is processed in the format of simple event visualization programs, histogram, and training resource. To work with the programs, you must have constant access to the internet. Visualization of events takes place in a specially created environment, the event display. The CMS event display, iSpy, can be used to visualize collision data. In the first lessons, students get acquainted with the device and the principle of operation of the muon detector. Main measurement tool, computer program, event display iSpy. Students are to examine DCs involving muon pairs and determine which events are iSpy meson candidates and then construct a histogram of mass counts for events that pass the purple trigger. Consider examples of tests offered to students in the course of the practical work. To be a candidate for iSpy, an event must have two muon tracks of opposite electric charge. In two tracks deviate in the same direction inside the solenoid located inside the Hadron calorimeter. They have the same sign, therefore they are not created as a result of the J-psi decay. Next test, opposite charges, quality of the muon checks. If two muons pass the charge test, analyze the J-psi probability by evaluating each muon track. If there are more than two tracks, rate the two most successful with the opposite charge. Record the score for each event in the datasheet. Calculation of the mass will become possible only after the evaluation of muons. Next, the student is advised to count how many events in her set resolved the same scores. Compare the results with other students. If the numbers differ significantly, discuss your scoring criteria and see if the scores need to be adjusted. At the stage of ascertaining experience, there was a study of methodological approaches to practical work in elementary particle physics. In particular, the work of students in studying the methods of experimental particle physics was studied. At the research stage, a starting experiment, training, and control were carried out. The effectiveness of the developed approach was evaluated based on the calculation of the coefficient of efficiency of mastering physical knowledge, determined by the formula of the slide. The main goal of the formative stage was to test the effectiveness of the proposed developments for the workshop in elementary particle physics. By the structure of student learning outcomes, the non-parametric Mann-Whitney U test was used to assess the difference between two small samples in terms of the level of the attribute. From table, it can be seen what were in a larger rack amount in the experimental selection. According to the table of critical values of the Mann-Whitney criterion, students of the control group are inferior to students of the experimental group in terms of the coefficient of efficiency of assimilation of physical knowledge of elementary particle physics. Our research showed what were the opportunities to study the operation of the mass technology device in the world, the Large Hadron Collider, due to the opening of access to a huge array of data obtained at the Large Hadron Collider and the development of information, the communication technology. The exploratory and experimental verification of the research results proved the expediency of the practical implementation of the developed methodology for the use of CERN services and data in the process of studying the physics of elementary particles. Thank you for your questions. We will be grateful for your questions.